Okay, so with this lab, we were given a network of 5 resistors, and the first resistor was in parallel. Then from that, a node was taken off where we had a 47 ohm resistor, and that branched off into 2 branches with a 51, and the other final branch is an 82 and 100. So in order for you to work on calculating and getting all of your resistance and everything involved, you had to condense everything. So the way to think of this is that if you were at the beginning of the circuit at the panel, as far as current is concerned, I mean, it doesn't think, but as far as the current goes, it takes whatever path it can take to complete a circuit. And at the panel, it doesn't matter how many receptacles you've installed, it doesn't matter how many lights are on the circuit, it's going to leave the panel with the maximum amount of current. So in order to find that out, you need to know what the total resistance is, and because it's parallel and series, it's going to do a series of combinations and splitting off, both voltage dividing and current dividing. So the first thing you had to do was take the last leg, the furthest point away from the panel, and condense it and simplify it, because essentially we're trying to get it down to a single resistor, because that's the amount of current that's going to leave the source. So in this circuit, the furthest branch away from our power sources are 82 and 100 ohms, and that forms a series branch. So we can condense that and have it appear to be a simple resistor in parallel. So we're going to take this and I'm going to copy it and I'm going to paste it. But what I'm going to do is I'm going to correct my circuit, because it's no longer 100 and 82, it's the reduction of 182 combined. So the best way to do this is to keep track of the compression that you're making. So I had, starting from left to right, the last two would have been R4 and 5. So now I've got the equivalent of R4 and 5, and that's going to be our 182 ohms. So once that's done, this other spot here, it's no longer in our equation. We'll come back to it, but right now we can think of it as being taken care of. It's no longer in our circuit. So the next step will be to start working on the next branch. All right, so since we have 182 and our next parallel is 51 ohms, it's simply a matter of saying, okay, I just need to know what the total conductance is and then get the reciprocal of that. Or we can simply say that R345 is equal to 1 divided by, and we'll put this in brackets, okay, so it's going to be 1 divided by 1 over 51 plus 1 over 182. So when we determine what 1 over 151 was and 1 over 182 and added those two together, then we simply divide 1 by that, and that becomes the resistance of R3, 4, and 5. So at this point, you should have got somewhere in the neighborhood of, let's get my calculator busy here. Okay, so when you take the reciprocal of 151 and you add it to the, you take 1 divided by 51 and add it to 1 divided by 82, you come up with 0.025, And when you take 1 and divide it by that, you come up with approximately 40 ohms. Now, if you got like 39 or 39.4, something in that ballpark. If you got like 80, you were probably off track. So now this means that the equivalency of this network of 2 resistors can now be reduced from that. And I can take this away from our circuit. Don't need that anymore. And I know it's no longer 51. I now know that my circuit is now 40 ohms. So R 345 equals 40 ohms. And now we're going to get to the next stage, which we can see is it's a new series circuit with only 2 effectual resistors, 47 and this 40 ohm resistor. So we'll take care of that next. Okay, so we've got our 40 ohm and we have a 47 ohm, so now I need to have a new equation. I've got to say, all right, I want the total for R 2, 3, 4, 5, and that is simply the addition of the 47 plus the 40, which gives me 87 ohms. So when I do that, that effectively changes my circuit again, where now this 47 ohm resistor is incorporated with our other one. So I can take, it's getting kind of crowded here, I'm going to put you up to here for a second. I can now take this, and let me see, let's do this way. Okay, you're off the table right now, and now I have 47 ohms, so I can just put in a simplified statement right here. I can get rid of this resistor, no longer in play. Thank you very much for playing along, and connect that across. And now this down here is our R2, 2, 3, 4, 5. And it's equal to 87 ohms, which now happens to be in parallel with this other resistor here, this 33. So that's the next step. We're going to reduce this again, so we have the equivalency of 1 resistor. All right, so now we're going to take and do the next step, which is basically we're now trying to calculate the R1, 2, 3, 4, 5, and that's going to be equal to 1 divided by 1 over 33 plus 1 over 87. Okay, so we'll calculate that out. Okay, so when you take 1 divided by 33 and you add it to 1 divided by 87, you come up with 0.041 or 4179, and now we're just going to divide that into 1, and we come up with 23.93 ohms. So roughly speaking, 24 ohms. If you had something close to that, no problem. And now what we've done is, like, we're going to take our big fat eraser, and nothing beyond this point exists. We're down to a single resistor, and it's no longer 33. Our resistor is now the R1, 2, 3, 4, 5. So now that we have the 23.9 ohms, we've got 5 volts, we can now determine the total current simply by taking the volts divided by, so our current is equal to our volts divided by our resistance. I started color coding stuff a long time ago, just so it makes it a little easier to see what you're attempting to accomplish. So once I've got that, then I should be able to get my total current. So we have 5 volts divided by our 23.93 ohms, and that gives us you should have got something in the neighborhood of 208, call it 209 milliamps. And from that, what we're going to do is we're going to start following that current as it leaves and goes into the circuit. We put the circuit back together again. So when the current gets to this first node, part of the current is going to go this way, and part of the current is going to go this way. And this, of course, when it's current times our resistance, that gives us a voltage drop. So we'll have a voltage drop across here, but we'll also have a voltage across here, because that resistor we said, thank you very much for coming out and having a nice day, it's now back in play. It gets inserted back into our circuit, and that's going to create a voltage drop that we're going to measure. And everything to the left of that, everything from this point over, is not going to see our 5 volts. It's going to be discounted. First come, first serve. Some of that voltage was consumed and branched across here. This is going to be 5 volts. But from that point forward, at this next node, that's going to have less voltage, simply because part of the current was disrupted, if you want to think of it that way, by the 47 ohm resistor. So we'll do that next. All right, so we know part of the current is going to flow down through the 33 ohm resistor. So what we've got to do is we have to calculate how much current's going that direction, because we now have a parallel circuit attached to it, and that makes it a current divider. So we have our 5 volts, because as far as the resistor is concerned, as far as the current is concerned, there's a 5 volt parallel that's pushing the 5 volt potential difference that's pushing the current through 33 ohms. So we take our 5 and divide it by 33, and you should have come up with something in the neck of 0.1515 forever, so we'll call it 152, or 152 milliamps. Now, at our store, we had our bank account, and we took our wallet out and brought some cash with it. So originally we had 209 milliamps to spend, and we've just spent 152. So the current flowing through R47, at this point, it's not really 47, it's actually the combination thereof. But we've gone to that first node, we're going to pass the current through there, and that's going to give us a voltage drop. So to calculate the voltage drop, we've got to subtract the 152 milliamps from the 209 milliamps. And if I go 209 subtract 152 gives me 57 milliamps. So going in this direction, all we have left over is 57 milliamps. And that's going to go through our R47, and until this is broken apart, our 345 is going to see the same amount of current going through it. All right, so to calculate the amount of voltage we're going to lose because of this small 47 ohm resistor, I mean, it's not that much. We've got to take our 57 milliamps and multiply it by 47 ohms. Now, if you're not thinking it through, that 57 isn't 57. It's 0.057. So when you use that, you will find by multiplying the two, you end up getting a voltage drop of 2.679, or if you decided to call that 2.7, that would probably have been close enough. But at that rate, that's the amount of volts that we now have to subtract from our 5 volts. So between these two resistors, this one's taking the full 5 volts, but this one is discounting it by more than half. So the voltage that is going to be applied to 3, 4, and 5 is equal to the 5 subtracting our 2.7, giving us 2.3 volts. That's all that's left over. So at this point, at this next node, we're only dealing with 2.3 volts. And again, the current is going to go in two directions. Change my color. Current's going to go this direction and this direction. So we can then calculate what the net result is going to be, especially when we get the current. We know what the current's going this way because that will tell us our 2 voltage drops on our last 2 resistor. Okay, so we've got to determine now the current that was being applied through our original circuit. We've got up here the voltage drop that we've lost from 47, and we're left with 2.3 volts. So to find the current, we simply have to take current is the result of voltage divided by our resistance. So we're going to take our 2.3 volts and we're going to divide that by our resistance of, this was 33, that would be the 51 ohms. And when we do that, we get 2.3 divided by 51, a whopping 45 milliamps. So now, since we have 45 milliamps going this way, we now need to figure out how much current is flowing this way. We also know that this branch is in parallel right now with these two because we've separated the 51 ohm resistor out. So now this is in parallel. So we should be seeing on this side here that same 2.3 volts. So we can calculate what the current's going to be, and it should be the current we had before. This current and this current should add together. So we'll take care of that next. All right, so two things. I did a kind of visual and verbal boo-boo. The current we got for 45 milliamps wasn't R4 because R4 is this 82. It should have been R3 because this is 1, that's 2, and that's 3. So I fixed my mistake. It's still 45 milliamps, but it's not for R4, it's for R3. R4 gets the same amount of current as R5 does because it's the current leaving this node sees a series circuit. So when you take the 2.3 volts that it's in parallel with R3, we now know we can divide that by 182 to determine how much current is flowing. So we have our 2.3 divided by our 182, and that gives us a paltry, tiny, insignificant, but still vital to this operation, that equals 12.6 milliamps. So when we take the next part, we confirm all our work. We just start working backwards to see if we can account for all of the currents adding up to this 209. So double checking our work, we take our 47 milliamps and we add the 12.6, and we get 57.6, which, given rounding errors, etc., you're right there where the other 57 milliamps. So we've accounted for the 57, that's taken care of. Now we can say, okay, let's take the 57 and add it to this 152 that the first resistor took, and we come up with 209, which is exactly the amount of current we are expecting. So all of our current flow is correct. Our voltage drops are correct. The only thing we need to know now is the voltage drop across our 82 ohm resistor and our 100 ohm resistor, which, knowing that we have 12.6 milliamps and it's only got one path, is simply a matter of taking the 12.6 times 82 and the 12.6 times 100, and that will give us our two voltages. So working on that, we'll take 12 milliamps and we'll multiply that by our 100. That's easy to remember, and that gives us, well, let me get my calculator because it's milliamps. We want to remember to put that 0 before we do the, so it's 0.012 times our 100, which gives us 0.12. Okay, so getting back to where we were, never hit the pause button. So we take our 12 milliamps and we multiply that by our 100 ohms, we come up with 1.2 volts. Then we take that same 12 milliamps, because it is a series circuit, and we multiply the 82 by the 12 milliamps, we come up with 0.9884 volts. So when we add those two together, we're at 2.1888, or call it 2.2 volts, which is ridiculously close to our 2.3. It's within what you would consider to be a reasonable, I mean, it's off by 0.1 of a volt. But we now know where the currents are all going. We now know where the voltage drops are all taking place. We've completely solved the circuit. So now what we can do is we can start, we've got all the facts and figures we need to populate the lab. But what we're going to do, we're going to go one step beyond that, because we're going to change the circuit. And I'm going to do a screenshot that shows all the voltages down to the nitty-gritty, and then we're going to take a look at that, and we're going to start looking at what happens to all these different currents and the way they're flowing. Okay, here is our larger network that we've done, and it looks a lot more complicated than it actually is. I've put in different voltmeters, so that just like if you had taken a meter out and started doing the readings, you do voltmeters across loads. So our first load, we've got the current flowing through it, but we need to know what the voltage is, and our first one confirms, yep, it's got 5 volts on our principal power, and we're getting 5 volts across our first our 33 ohm resistor. So at our node, we can see there's our total current of 209 milliamps, and it gets split off. And their calculations show there was 2.7 volts across our 47 ohm resistor, and there was 103 or 1.033 volts going left over. Not sure why they got that different than we got. That 44 milliamps going this way, 2.29 volts dropped across that. And then this one here, we had 103 ohms. Oh, I know what I'm reading. That's because this is the voltage drop across our first resistor. This is the voltage drop across our second resistor, and we put that together and we come up with 2.29. So when we look at all this networking, we can see the different voltage drops. That's 2.29, which is the same as adding to that. This 2.29 plus our 2.7, you add that, we come back up to our 5 volts. So everything actually makes sense. You can see that the different amp meters are showing we got 151 milliamps going here, And if you add this up, we get the same. This plus these ends up giving us our 209. Everything is exactly the way it's supposed to be. But I've put in my little demo here some switches. And depending on which switch we open up, we can actually change and watch what happens to all our currents. And our voltages are now changing, because I've opened up one of our parallel branches. So this is no longer in the circuit. We now have a circuit that has 3 resistors in series in parallel with our 1 resistor. So I'm going to put that back, and I'm going to take out, say, this 100 ohm. Now I've got no current flow going through this entire branch because it's open. My voltage has changed on my 51 ohm, and the current is all different. We've dropped our current down to 202. Turn that back on. There we go. And back up to 209 milliamps. If I open this one up, come on, you can do it. Current drops down to 151 because it's only got 1 resistor. So the second part of the lab was to get you to swap out some of these different resistors. So what I'm going to do, this was the part of the lab that was called the alternative universe. So I'm going to change this up, and we'll take a look and see what happens to our entire network. Okay, so the first thing that was swapped out, instead of this 33 ohm resistor, just take that, set you aside. We're going to grab the 100 ohm resistor, and we're going to stick that there. And the 33 was going to replace our 47. So we'll put that up here. And the 47 was replacing the 82. And the 82 replaced the 51. And the 51 swap places with the 100. So that's our new circuit. Now, none of the numbers have changed because it hasn't run the simulation. But let's just take a look now that everything has changed and see what we come up with. And pop, everything changed. Notably, the total current dropped down to 114 milliamps from the 209. And that makes sense when you figure that the rest of the circuit, when you start combining it, is made up of smaller components. That 100 has been taken care of on its own branch. It's getting the full 5 volts. But the 47 and the 51, that's close to 100, but it's certainly not 182. And when you add that in with the 33 and the 82 in these 2 positions, it completely changes the entire dynamic of the network. And if I were to take this one out, again, we see that's dropped down, and just swapping these 2, let's see if that makes a big difference. We've climbed a little bit. We've climbed up a little bit more. So you can see that with combination circuits, it really impacts the amount of your voltage drops and your current drops. And turning something off of a circuit, you can see your current drop, which you expect because you don't have as much of a load on it. Each time you open up a branch, you're going to be changing the current. And the same thing goes on dynamically in even in something as simple as a house circuit. It's just you need to be aware that just because you've turned the switch off, you've changed the amount of current being drawn, but you're still exposed. The different parts of the circuit are still going to be hot, which is why the best thing to do is shut it all off. You don't have to worry about it anymore. Anyway, that's basically what you were asked to do. And when it comes to the midterm, there's going to be a couple of questions that you're going to look at 2 different networks or the same network that's been changed. And just by the same approach that we've done here, you can then determine what has changed and what needs to be fixed, or you know, what's happening by changing just the order of operation with respect to the placement of the different loads.